All right, last section on orbital mechanics. We're going to look at the special orbit types. So we've got all the different things we researched before, the different ways to talk about the different orbits, the 6 different ways to do that. But there's some that just fit into categories for us. So what we've got first is LEO, or low Earth orbits. No minimum altitude. They're relatively close to Earth. Short orbital period's about 90 minutes. Make many revolutions a day then. Limited swath of areas, so they can, what can they view on the Earth's surface we're going to look at. They're all manned for space missions, except for the lunar missions where there's LEO. Many Earth-observing satellites for weather. And why is it that? Just because they can look at greater detail for where they are. So International Space Station is an LEO. Its orbit is about 350 kilometers off of the Earth itself. There's geostationary. Geostationary satellites remain over one location on Earth in a special orbit where period exactly equals 1 day. The altitude is about 22,200 miles. Inclination is exactly 0 degrees. So this has the same period. So as the Earth rotates, the satellite rotates with it. So it takes a picture of the same place at the same, like all the time. It's always playing and looking at that same location there. So if you're looking at something like that, that would be good. Trying to look at for your satellite dish, you don't want to be off on another side of the world at a certain time. You always want it highlighting over that specific area to be able to look and circle through. So that's where our geos would go ahead and look at for us. So geosatellites only exist directly above the equator. They can reach up to about 7 degrees north and south just by the power of them to cone out, used for communication or relay station in Earth itself. So geos, only one altitude with a period of 24 hours. So here's a nice picture of all of them. The geostationary orbits are in a ring around the Earth. The ring is called the geostationary belt. Geostationary belt has limited resource or space that's in there. So GeoBird, when it dies, it's removed from its slot to make room for another one that's in there. So that has a little bit of power left. It just kicks out a little bit of power, spits it out of that circle, and it goes and moves on. Difficult to orbit exactly 24-hour period with zero inclination. They have a little bit of inclination that's there, so they'll drift north or south of the equator or east and west with imperfect periods. So that's where they'll just do orbital burns to send those back into their correct location to go through, so you can kind of see that little bit that's there. So if you're noticing that your satellite's off a little bit, means Dish TV's got to get up to their satellite, do a little bit of burn to put that back into the correct path that's there. So the ground trace is projected out to geostation altitude. Large inclinations run out the station, so this keeping fuel. Sine wave orbits are being drifted to a new location that's there. And then the orbit color participation in the data sharing. So going through and looking at all the different ones, and they're moving, and what each one of those movements tell us different things for it. So how can you tell which direction is south if you're lost in the middle of an urban area? You look at the satellite dishes. All satellite dishes in the United States would point south down towards the equator. The Mali used geometrical satellites for communications, pose severe problems for Russia since it is above the 70-degree altitude. So therefore, they created the Mali orbit for long-term communication over the northern land itself. So looking at that orbit that's going through there, highly inclined and highly elliptical orbit. The high inclination covers northern Russia. The high eccentricity of it, so large apogee, very slow velocity at the apogee itself. If the apogee
Please come to the assistant principal's office.
Over Russia, then the satellite hangs over Russia. That's there, so it slows down, and then speeds back up as it comes back. So here's the ground trace of it. It looks different than most because of that long hang time that's there, so it kind of loops over the same position, meaning the Earth is moving faster than the satellite itself. So as it's going through, here it's tracing where its position is to the ground trace. You can kind of see why we would have a problem with that orbit, because not only does it spend a long time over Russia, it also spends a long time over the United States on that path itself. So that's where some of the space laws and things exist for us. So polar orbit, because the inclination of polar orbit is 90 degrees, satellite in the polar orbit will eventually pass over every part of the world. This makes polar orbits well suited for satellites gathering information about the Earth, like weather satellites. A special type of polar orbit called the Sun synchronous orbit passes over the same part of the Earth at roughly the same local time every day, so therefore I can take the picture and see. So if we're going over North Korea and looking at their military or their nuclear stuff, we can take a picture every day to see what's moved and what has not with that. So constellations is just a grouping of satellites for us. So GPS is a type of constellation for us, so therefore they can all group together and give us data, or if one goes down, the other ones would still exist for us to be able to read and work with. So now that you have gone through all that, you can go ahead and you can do some different research into different stations, what type of satellites and what are things use it, and then there's software where you can model those and kind of see it itself. So you should now be able to go into the section of 234 and complete that assignment.